Hey everyone, I was looking at your chronos for this week, and there's a problem on there. There's a few problems on there that a few students have struggled with in the past. So I wanted to make a short video working through a couple examples of a similar problem so that you kind of have an idea of where to start with this. So let's say you're given a trigonometric expression equal to cosine cubed of theta. Right? And let's say you're going to be given a bunch of options. I believe in Cronus you're given 8 different options of other trigonometric expressions, and you're asked to use trig identities to either verify or disprove all of those 8 functions being equal to the original function you were given. So let's say here you're given cosine cubed of theta. And let's say one of the options you're asked to verify equality with is going to be cosine cubed of negative theta. All right, we want to figure out if this equals cosine cubed of positive theta. All right, and ideally what we want to do is verify that these two expressions equal for all angles theta. Not just say the angle 0 or the angle pi over 2 or a specific one that you plug in, but we want to verify it's equal for any angle theta, whether it be one of the 16 you memorized from the unit circle or whether it be some weird one like pi over 17. All right, so we want to work with these expressions without knowing what theta actually is, without plugging in anything for theta. The way you do that is through the trig identities in your lecture notes and lecture videos. So you do want to start memorizing those. We'll use them a lot throughout the entire semester, especially once we get to module 9. All right, so we're looking at this expression cosine cubed of negative theta. All right, remember by definition, whenever you have exponents with trig functions, this just means you have the value cosine of theta, and we're going to cube it, cosine of negative theta, and we're going to cube that. All right. So we want to somehow turn this into cosine of positive theta cubed. All right. Anytime you have an input of a trig function that's negative angle like this, you're going to have to use even and odd identities. All of your 6 trig functions are either going to be even or odd. Cosine and secant are even. All the other trig functions are odd. So by definition, an even function, it means that cosine of negative theta equals cosine of positive theta. That's by definition of even function. And cosine we know is an even function. All right, and then we're done. We have verified that cosine cubed of negative theta equals cosine cubed of positive theta, just using definitions of exponents of trig functions as well as the even properties of cosine. All right, so that one's easy. Let's look at a more complicated example. Let's say you had the expression cosine of pi over 2 minus theta divided by secant of pi over 2 minus theta. Oh, the secant is squared. Right? I want to see if this expression equals cosine cubed of theta. All right. All right, so let's work with this in pieces. Let's first look at the numerator. The numerator is cosine of pi over 2 minus theta. Anytime you see the input of a trig function is pi over 2 minus theta, not negative theta, that's different. That was the even and odd identities. But if the input is pi over 2 minus theta, then you always want to use co-function identities. They're the only identities that change the input from pi over 2 minus theta to theta. And that's what we generally want to do. All right. So the cofunction identities, if you know the trick, they're a little easy to remember. They always change pi over 2 minus theta to theta or vice versa. And they always either add or remove a prefix co from the name of the trig function. So here we have cosine of pi over 2 minus theta. It already has the prefix co in front of cosine. So if you remove that, what do you have? Sine. So by cofunction identity, cosine of pi over 2 minus theta is sine of regular theta. Right? And we can do the same thing to the denominator because, again, the secant squared pi over 2 minus theta, it's just secant of pi over 2 minus theta, parentheses squared by definition. So you just apply it to the inside and then square it. Secant does not have a prefix co, so you add one when you use the cofunction identity. This becomes cosecant of regular theta, and it is indeed squared because the secant before was squared. That did not go away yet. All right, so we've made some progress. We've simplified the expression. Now let's continue. We have a sign in the numerator. I don't know if we'll be able to do anything with that, but we have this cosecant in the denominator. And the expression we want to get down to is cosine cubed. There's no fraction there. There's no denominator. So let's see if we can get rid of the denominator altogether and not have to deal with fractions. Fractions are icky. Let's try and avoid them if we can. So let's see. We have cosecant, and it's a denominator of a fraction. So let's think, what identities do we know that can use cosecant and also converts fractions to non-fractions, or vice versa? Well, there's one kind of identity like that. It's the reciprocal identity. The reciprocal identity, I'll write down for you. There's a few of them, but the one that uses cosecant is like this. It states that cosecant of an angle equals 1 over sine of that angle. So we can use that here, all right? We'll turn cosecant into 1 over sine. Ooh, and now we have fractions inside of fractions. Ugh. All right. Well, first let's distribute that exponent so we can just have a division by one fraction. So this will be sine theta over, whenever you square a fraction, you square the numerator and the denominator separately. So this is 1 squared, or 1 over sine squared. Right? And it's still a fraction of a fraction. So we're going to have to deal with that somehow. All right. Fractions are just division. So let's rewrite this. Let's do sine theta division symbol 1 over sine squared theta. All right, and you learned how to divide by fractions in grade school. So you keep the first expression, flip the second fraction, and change division to multiplication. So this is sine theta times sine squared theta over 1. Anything over 1 is just itself, so I'm just going to write it as sine squared theta. So this ends up equaling sine cubed of theta, because you have a sine of theta times sine squared of theta. All right, sine cubed of theta is definitely not equal to cosine. Excuse me, sine cubed of theta is not equal to cosine cubed of theta. You can see that if you want to by plugging in any angle where the sine does not equal cosine. So for example, you could try the angle, let's see, let's just make it easy. Let's do pi over 2. All right, cosine cubed of pi over 2, right? Cosine of pi over 2 is 0. 0 cubed is 0. Sine cubed of pi over 2, well, sine of pi over 2 is 1. If you cube it, you still get 1. So for the angle pi over 2, these two expressions are not equal. Therefore, we cannot make the statement that these two expressions are always equal no matter what theta is. And remember, that was our goal. We wanted to make the statement that, hey, no matter what angle you try and plug in, these two expressions will always end up equaling each other. You can prove that it is true with identities, but you disprove it if it's not true with plugging in an example. Now, generally, you want to try one or two angles if you're trying to disprove. So if you really think two expressions are not equal to each other and you plug in an angle, they may come out the same for that specific angle. Doesn't necessarily mean they're always equal. It just means they're equal for that angle you chose to plug in. So you might have to try another. Pi over 6 and pi over 3 are really good angles to plug in because neither one of their sines or cosines are 0. So if one expression gives you a negative and the other expression gives you a positive, you don't have this false impression that they're equal because negative 0 equals positive 0. So you don't have that issue with pi over 3 and pi over 6. Another issue would be like pi over 4. You may want to try to avoid the angle pi over 4 just because the sine of pi over 4 is the same as the cosine of pi over 4. So you may have an expression like this where we had sine cubed of theta and cosine cubed of theta. If we'd have plugged in pi over 4 as a test angle for these, we would have gotten the same expression for both because sine of pi over 4 equals cosine pi over 4. So generally avoid pi over 4. Try pi over 3 and pi over 6 if you're trying to prove that two expressions are not equal. And I think that'll disprove most expressions that aren't equal to each other. But if they are equal to each other, you can't prove it by plugging in a bunch of angles. That doesn't prove anything. You need to use the identities. All right, so this is to give you an idea of what you're supposed to do for these problems in Chronos. Hope this helps. Message me or come to office hours if you have questions.